This video will provide a short overview of how to work with vectors. It's going to be very important that you know how to build up and deconstruct vectors because that's going to play a very large part in many of the problems that we work with in this class. Hopefully, you will remember the difference between scalars and vectors, as we've already discussed these in class. Scalars have magnitude only, so they only have a number associated with them, whereas vectors have both magnitude and a direction. Here we see some examples of scalars include distance and speed, whereas the corresponding vectors would be displacement and velocity. Let's take a second and look a little more closely at one of these examples. If we look at both distance and displacement, we can give an example of distance as 5.0 meters. However, when we do that, that doesn't tell you in which direction that 5.0 meters is. It could be any direction. When we make it a displacement, a vector, we give it a direction as well. So we have 5.0 meters to the east, and that is a specific direction and distance. Adding vectors in one dimension, whether horizontally or vertically, is a pretty straightforward venture. All you do is simply add the two vectors together because they both lie along the same axis. Here we see we have two vectors, one of 5 meters and one of 2 meters, and to add them together we simply get 7 meters. Subtracting vectors just involves subtraction. You simply subtract 5 minus 2 to get 3 meters. Notice that the second vector is pointing to the left. Addition and subtraction of vectors vertically works in the same manner. Here are two examples. Once again, notice that when you subtract vectors, the second vector, the one that is being subtracted, points in the opposite direction. Adding vectors in two dimensions is a little more difficult and involves a little bit more math. To give an example of how to add vectors in two dimensions, I'm going to use two volunteers, Bob and Rainbow Dash. Here we have Bob getting ready to walk down a city street. First, Bob is going to walk 3 blocks to the east, and then he's going to walk 2 blocks to the north. If we were to draw the horizontal and vertical vectors, it would look like this. Now if we were to get Rainbow Dash to fly a straight path from where Bob began to where he ended, it would look like this. The capital letter R stands for resultant, which is not an actual quantity in physics, but just means the sum of two or more vectors. The resultant actually stands for things like velocity or acceleration, displacement, and force. But for right now, as we're doing the math, we can just call it R. We can use the Pythagorean theorem to find the magnitude of the resultant. However, vectors are more than just magnitude. They also include direction. For that reason, we need to find the value of this angle here called theta. To do that, we just find the inverse tangent of the opposite over the adjacent, which in most cases will be the y value, or vertical, over the x, or horizontal value. Combining this with our value for the magnitude of the resultant, we get a displacement of 3.6 blocks at 34 degrees northeast. Now notice I don't write that as delta x for the displacement because this is not strictly horizontal or vertical. So instead I write distance with an arrow over it to indicate it is a vector. Also notice that I have to include the map direction of northeast in my direction. Using the Pythagorean theorem and the inverse tangent, it's quite easy to add more than two vectors. Here we see Bob traveling 3 blocks east, and then 2 blocks north, followed by 4 blocks east. If we have Rainbow Dash fly the same path, we can see that we would get a resultant that looks like this. The easiest way to solve problems that have more than two vectors is to use a T-chart, where you list all the horizontal magnitudes in one column and all the vertical magnitudes in another column, and then add them up before using the Pythagorean theorem and inverse tangent. Notice that it does not matter which order you add the vectors in, you will always end up with the same resultant. Here's a third way of adding up the same three vectors, going north first, and then the two directions to the east. We can then simply use the Pythagorean theorem and the inverse tangent to get a displacement of 7.3 blocks at 16 degrees northeast. Just a quick note about choosing the angle whenever you're doing a problem. In nearly every problem we work, probably 90 to 95%, the angle should originate on the x-axis, the horizontal axis, and then move up towards the resultant. Here you see 4 examples of the angles you would choose in order to do your calculations using your inverse tangent. Now that is not to say you will always choose that angle. Here we have a telephone pole with a guide wire stretching to the ground. If I wanted to measure the angle from the telephone pole, I would be measuring it from the vertical axis. So I would need to make sure my angle began on the telephone pole and extended to the guide wire, which would be the resultant. Notice that my phrasing for the direction is a little bit different. Since I come from the vertical axis, I just list it as 45 degrees from the vertical. I cannot use my map directions when I'm coming off of the vertical axis. So we have just seen how we use 2 component vectors, the horizontal and the vertical, to find a resultant and then calculate the magnitude using the Pythagorean theorem and the angle using the inverse tangent. However, most things in life do not occur strictly along the horizontal and vertical axes. For that reason, you need to learn how to break down a resultant vector that is already at an angle into its 2 components. Here we have a resultant vector directed at an angle theta, and here are the 2 horizontal and vertical components. Notice that we label them as r sub x and r sub y. I'm not going to show you all of the trigonometry involved, just the final equations that allow you to calculate these 2 components. I suggest that you memorize these 2 because you will be using them quite often. Here is a quick example of how a vector directed at an angle can be split up into its components. Here we have a human cannonball that is shot forward with an initial velocity of 18.0 meters per second at an angle of 42.0 degrees. Here's the horizontal and vertical vectors of his initial velocity. Because the kinematic equations that we have learned work only in the horizontal or vertical direction, we cannot use them for vectors that are delivered at an angle. So we use the 2 equations, that v sub x equals v cosine theta and v sub y equals v sine theta, to calculate these 2 components. I hope this video has helped you to understand vectors a little bit better. As we begin working in Chapter 3, we'll start off with practicing the skills demonstrated in this video before moving on to 2-dimensional motion.